Hi, my name is Mark Lepetis, and I'm the Senior Editor of Semiconductor Manufacturing and Design, or SemiMD. I'm here today with Subramani Kengeri, Vice President Technology Architecture at GlobalFoundries. So, Subi, we're seeing some new and interesting developments in the world of scaling from 28 nanometer planar to 20 to 14 nanometer FinFETs. What are the general overall challenges that you're seeing on this front?
Thanks, Mark, for the question. It's a very interesting question. So if you really look at what's happening on the scaling, right, from 28 planar to 20 planar, and now we have the 14, which is truly a 20 nanometer backend with a FinFET device that we have put in, there are some very interesting challenges which forced us to do what we did. So the first thing is the cost aspect of it. I mean, everybody have been talking about the cost. Generally or historically, customers have been used to somewhere in the range of about 30 to 35%, die cost reduction on a node-to-node basis, and that was all okay when the world was planar, right? But then also the optical, was able to get us, on the historical scaling path. But then now, if you look at two things, that is really a challenge. One is the planar is almost dead, so you got to do something different, and you have to do it very cost effectively. That's number one. Number two, the optical, it's also reaching certain limits, and to move to another option, let's say EUV, is not a straightforward option because there are some challenges, there are technical challenges to make it work, and doesn't mean just because it's going to work it's going to be cheap, because there's huge investments that have to go in there. We have to amortize that and get back all the investment and amortize that over the die cost. So there are challenges there. So what we did, talking to all of the key customers, is we wanted to extend the life of planar in a very creative way, right? So we took all of the learning on the 20 nanometer planar, okay, which is still optical, no UV yet, and then plug in the advanced FinFET device, right, with the front end being FinFET basically. But we didn't just stop there, right? What we did was we made that FinFET a true 14 nanometer class FinFET. So the front end was still advancing to the next node, more or less, but the back end will leverage everything that was already there on the 20 planar. This combination is very, very attractive because it solves a number of issues and also accelerates the time to market on the next node.
Subi, we've had a number of discussions about power consumption, voltage scaling, and those kinds of issues. GlobalFoundries talks about something called PPA. Can you explain what that is and some of the issues with voltage scaling and power consumption?
So if you look at FinFETs, right, one of the important things here is you have huge drive current, but when you say you have huge drive current, it's not all that easy to manage that, okay, in the same area, so which gives rise to the power density problem, which has to be solved before we can make FinFET usable. But let me say that the power density is one of the critical issues that comes with FinFET. So if you look at some of the architectures and the FinFET solutions that are available out there, not all are created equal. If you haven't thought through the FinFET power density issue, then the products can fail in the field a year and a half later because of reliability. So one of the critical issues is really the electromigration. Right now with FinFET, driving 50, 60, 80% more current density than the planar equivalent, okay, your metal in that standard cells, for example, or the memories, have to be able to drive that huge amount of current in that small area. And this was not a problem in the past because things were scaling and you were improving your resistivity, you were improving your EM capability. But now if you're going to reuse all of the same back end and the middle of line for all the good reasons that we just talked about earlier, you still have to solve the electromigration problem. So one thing that we have done is we have thought through that very, very carefully, and the whole idea here is to be able to enable wider power rails in our technology architecture through the right choice of design rules and the litho solutions. So that's one thing. Okay, so the power density is a critical issue. If people haven't thought through that, FinFETs will fail. The second one is the voltage scaling. that is very different from the planar world, right? Because the voltage scaling was really dead on planar because you could not bring down the voltage below a certain point because of the headroom issues, because of the subthresholds and the short channel effects and all the standard issues. With the fully depleted device on FinFET, gives you a huge amount of voltage scaling. Now, what is more important there is to enable the low voltage operation, but not at the cost of performance, right? Because if you're going to give up the performance significantly when you're dropping your voltage, then there's not enough benefit. So we have studied the markets and working with our key customers, we have optimized the FinFET with the 14XM to make sure that when you drop the voltage and performance curves still meet all the requirements of our key customers in their applications, and dropping about 100 to 130 millivolts without losing any performance is a significant advantage that FinFET gives you.
Subi, you've discussed a bit about lithography, the interconnect, and some of the power issues. Let me ask about some of the design issues in terms of what kinds of challenges for layout, or perhaps in double patterning, triple patterning, or what are the perhaps your potential customers going to encounter on those fronts?
So talking about the design issues moving from planar to FinFET, right, it is a learning experience for almost everybody. But what we have done is in the last 2 years, we have thought through some of the technology enablement and the design enablement pieces. And we have also worked with some of our key customers and looking at some of the key applications. So if you have to summarize, I mean, there are a number of issues moving from planar to FinFET in terms of design. But if I have to summarize, some of them are related to the quantization effect of the fins. So when designers were always used to drawing, whatever width of device they wanted to do to optimize and fine tune, the creative designers, they want to go optimize to the nth degree, which is good, but that's not possible on FinFET. Right now you have fixed granular, sizes of the devices, and that's determined by the fin pitch. But one thing that we have done is we are offering a 14 nanometer class fin, and therefore the fin pitch is more granular or finer than the rest of the industry. So, which is at 48 nanometer that I've already talked about in some of the previous discussions. So, it does give you some additional granularity compared to the rest of the world, but not as much as your planar device, which is one of the limitations of FinFET. The second one is you have to be extremely careful about your extractions and the RC effects, because of the 3D effects and the neighboring fins. You have to take into consideration every bit of the parasitics and the new parasitics that are coming in. Of course, we have worked with our EDA vendors to ensure that all of them are modeled very, very carefully, but we want to make sure that even our designers are taking into consideration all of that. The third one is when you look at the advantage that the FinFET gives you, like I just talked about in terms of the voltage operation, it does allow a wide range of voltage operation, right? One is you can drop the voltage 100, 150 millivolts. On the higher end, you can also go much higher till your reliability limits, which immediately allows you to give a wide operating range from a design point of view. And it's up to the designers to change their design methodology and be more creative to take full advantage of this wide operating range in their power management schemes. I mean, they're all used to using variety of power management schemes, the voltage domains, the power gatings, to whatever else, right? Now here is another additional wide voltage range, wide operating range tool that they have with them that they can use to their benefit. The last one I would say is the analog devices. For example, it now is far better. If you look at the planar to FinFET, suddenly because of the fully depletedness and the variability being much smaller, the mismatches being much smaller, you have a fantastic analog device today. If I have to put a rough estimate, it's almost like you have a 65 nanometer class mismatch device, which is always better, compared to like a 20 nanometer analog device would be worse, right? As you see, going from 65 to 40 to 28, the analog devices started becoming worse and worse. But now you can go back to a 65 nanometer class analog device with a 14XM process. So it's up to the designers to take real advantage of that. So there are some very good things. There are also some things that they have to watch out. But that's all the good things and the bad things about FinFET.
Subi, given that we're seeing delays in EUV and lithography remains a major challenge, and perhaps if we go to multi-patterning, it'll be quite expensive. Could we ever see the FinFET structures, instead of going down the Moore's law, go up to say the 28 nanometer, 20 nanometer, so on and so forth?
There are definitely challenges in bringing up EUV to production and making it cost effective, but that doesn't mean the world is going to stop, okay? So the way we look at it is the following. When would the world or the customers move to the next node? It's not just the number, it's not 14, it's not 10 nanometer, it's not 7 nanometer, that's just academic, right? In reality, the customers have to see the value, okay? Now the value doesn't necessarily come purely from dollars, even though, yes, that's a big piece. The way to look at it is the power, performance, and cost. At least you look at that together, the integrated metric, right? And that's exactly why, even though it's the 14XM or the first generation FinFET in the foundry world is really a 20 nanometer backend, customers are jumping to that because there is significant power advantage, there is significant performance advantage. So I really don't want people to think that the only reason customers are going to move to the next node, whatever that node is because of cost. No. Now, having said that, we are doing certain things to be prepared to take full advantage of EUV as soon as it becomes available. For example, not on 14XM, but on the next node, we are keeping, and we haven't disclosed this in public in many places, but I'll give you a little bit of hint. We are keeping our ground rules migratable to EUV. Now, what that means is we can let our customers and product designers design the chip with optical rules, okay, but when EUV becomes available, you can take the same GDS straight into EUV without making any modifications or redoing or retaping out. Okay, that does have some trade-offs and things that we need to think through upfront on the optical rules, because you're going to make some trade-offs to be compatible to both. But having thought through that, it's a one-time effort, but once you do it, that's the right way to do. That's the first thing. Second part of your question was, would FinFET go into 28 or previous nodes? It's a very interesting question, because honestly we have thought through that for the last several, I would say about 18 months or so, because when you look at the analog and the RF and the MEMS and the mature technologies, how would they benefit from FinFET, right? And when we think through it, there's a lot of value, but that is a highly cost sensitive market. Will FinFET with high-k metal gate in it, will it be affordable? Does it make sense? Is some of the things that we are analyzing, but purely from a performance metric or from a product level metric point of view, it's a great opportunity. We're still looking at it.
Subi, thank you very much for your time.
Thank you very much, Mark.